record both versions. Yeah, thank you for reminding me. All right. A couple of announcements. Actually, a lot of announcements. Exam 3 is next Thursday, so it's the day before spring. We go on spring break, essentially. It'll be chapters 26 through 28, and basically I have 3 days, essentially, to lecture on chapter 28. So I should be able to get done easily, okay? The chapter 28 web assignment is doing the 24th. Hopefully you can get it done before that so you can spend some time getting ready for the exam. The capacitor calculation worksheet is due on the 18th, and then the other one's due on the 21st. Now remember, if you submit both and you get 100% on both, then you get 20 out of 10 points, okay? It's just good practice, because the material on here is not only important for capacitance, but it really helps you to go back to the previous unit, okay? Because we're not going to really see that much on the previous unit as we go through the semester, because I don't have a final. One of the problems I'm not doing a final this semester. I mean, when we talk about Faraday's law, you will have to recall some of the information from these past 2 units, but you won't have, for example, a specific test problem on Gauss's law coming up. So.
Hey, Professor, if it's not too much of a delay, can I ask you a quick question about one of the homework problems?
Sure. Okay, let me finish going through this list, and then. Okay, just give me a second.
Yeah, go ahead.
Okay. The Ohm's Law Lab, I made it the 21st because I realized, Thursday I'm going to talk about part 4. Part 4 is a little long. It's not that long. And so I gave you till Sunday to do it. I'm expecting you to have the first 3 parts done like by tomorrow night. Okay. If not, if you don't have them done by tomorrow night, then it's your problem that you're behind. Okay, because I warned you. And there is a video that I emailed to you folks on the Ohm's Law Lab that Tyler made for us, and it actually goes through part 4. So you can get ahead and get started on part 4. But I have a few things I need to say for that part. And then one last thing, I'm trying to get all this stuff done before spring break. So the only thing you're going to be dealing with over spring break is the lab after this one. There won't be any web assignment, there won't be any worksheets over spring break. Okay, and it mainly is because we have the exam right before spring break, okay? So the only thing you'll have to worry about is the DC circuit lab. So go ahead and ask your question on the homework.
It's for number 10, part B, where you have like the system of 4 plates. Or, well, actually in part B, you only have 3 plates, right? The first and second plate are, in their positions, and then you bring the third plate next to those 2.
Okay.
And it asks you to calculate the work required to do this. And in my head, it makes sense for me to calculate, the potential energy, the change of potential energy from the first plate to the third plate and from the second plate to the third plate, but that doesn't get you the right answer. You also have to consider like the first and second plates, but I'm confused about why.
To put the third plate there?
Yeah.
So let's assume, basically the way I would do all the parts is to say, A, B, and C, to say, okay, let's say they're originally very far apart. How much work does it take to assemble that system of plates? And I did a problem similar to this with point charges in chapter 25. So I would say, okay, I'm sorry?
Can I interrupt you really quick? So I know the answer for part B is 0 because I got it. I kind of just guessed that. But when it says suppose the plates were initially very far apart and then the first and second plates are then placed at their locations. I assumed that meant that it was like that the situation started with that. Not that I also needed to include the work done to put those 2 plates there. If I did need to include that, then I understand the problem perfectly.
Yeah, the first two plates are there already.
Okay, well then,
Because it's only
I'm
asking
confused.
how much work is required to put the third plate there, right?
Right, so it doesn't make sense to me that the answer is 0.
But it's asking about the third plate only.
Right, yes.
Say, what's the field? So here's the two plates that we placed, okay?
Mm-hmm.
And this one's positively charged, and this was negatively charged. What's the field here?
0.
0. So
Okay.
there's no work
Yeah.
done, right?
Yeah, okay, thanks.
And yeah, that's really it. It's the same as putting the first plate there. The first plate requires no work.
Right.
Okay. That okay then?
Professor, can I ask a question on the same problem?
Okay.
So, like, I for part A, I asked Tyler for help, and he said he could find the energy stored by taking by using the equation 1/2 times the charge density squared times the area times the distance between the plates over epsilon naught, and then multiplying that by 3 to get like the to get the one for like each, for I guess for all 4 of the plates. And so I did that, and it said I got the wrong answer.
Well, but yeah, this is what you got to do, and this is what I was referring to. How much work does it take to put the first plate there? There's no field.
Wait, are we assuming it's like weightless?
Yeah, let's look at it this way. The gravitational force is negligible compared to, well, even if the gravitational force is negligible compared to the electric force, number one. Number two, if these 4 plates are isolated, there's no gravity if I put the first plate there. Right?
Oh, okay.
So now I put the second plate here. So you got to do them one at a time. How much work does it take to put the second plate there? Well, you're doing work against this field. Okay, you're doing work against this field.
But if it's the opposite charge, isn't the field going towards or isn't it pulling the plate towards the other one?
Yeah, so the work that you do, this one's oppositely charged, but this thing is positively charged, right? The field due to this guy is like this, right?
Yeah.
Okay, you're doing work against this field.
Yeah, but if the other plate's negatively charged, then aren't you doing, or do you mean like to hold it apart from the other plate, you're doing work?
Yes. Well, just to put it there.
You mean because it's pulling the negatively charged plate towards the positively charged plate, so you have to go against that force, right?
Yeah, that's true.
Okay, so that's what you mean.
I mean, it's the same thing as that if I have a positively charged particle here, how much work does it take to put a negatively charged particle here? I mean, that's what the answer. I mean, that's the expression.
Oh, okay.
Right. That's what it's asking for, right? And you can write it in terms of sigmas. And really, we wrote an expression for parallel plates. That looks like that. Right, the field is going to be given by this whatever the field due to this plate is. Now, once you've set this up, what's the field out here?
Oh, is it 0?
Yeah, so to put the third one in place requires no work. So essentially what you have when you're done, and I can answer this more of this question after class because this is kind of a long, I didn't expect this question. This is a little bit of a long question. You end up having 2 plates. All right, you basically have 2 plates, right? I'm sorry, 2 capacitors. You have to, this requires work and this requires work, all right?
Yeah. Oh, so
Okay.
you're only multiplying it by 2 then? Because there's...
So it's the energy in this plate and the energy in this plate times 2. I'm sorry.
Oh, okay.
The energy in this capacitor and the energy in this capacitor, right? You sum them and you're done.
Oh, okay. So I guess I'm just confused because on number 7 I did it the way I did it the same way on part 7 and it said I was right. I guess the capacitance of the 4-plate system. You know, yeah, I guess I'll just
Yeah, but that one's that's asking for the capacitance though, right?
oh yeah. Yeah, so this is different.
Yes, because this one's asking for energy.
Oh, okay.
Okay.
Thank you.
If you have more questions, ask me after class on this one, because this one's kind of a long. The problem is kind of a little bit long. Okay, but I can answer the question afterwards. Okay. I'm sorry. There's a few comments in.
I said thanks.
Oh yeah, sure, welcome. Christopher, that was number 10 on the homework, and a couple of questions. The e to the when in WebAssign, that's the same thing as this, because WebAssign doesn't do superscripts and subscripts, just like your calculator. Okay. All right. So if you have more questions, I can use some time at the end of class and I can answer your questions. Unfortunately, I need to proceed, but I can make myself available. What I want to do today is do a couple examples with capacitors and dielectrics, and maybe they'll help with the homework. And I want to do DC circuits involving series and parallel and talk about internal resistance. We've been talking about capacitors, and I've talked about this, but I want to list out a few applications of capacitance in real life. So I think we brought up the defibrillator the other day, random access memory. Okay, the electronic stud finder. And really, the electronic stud finder, all it does is find, basically measures the change in dielectric. Kai, we're going to talk about RC circuits probably Tuesday. Okay. So this is an electronic stud finder. If you've never used one, this is to look for the studs in your wall. Okay, your 2x4s in your wall. So basically what you do is like mine has a button on the side. Okay, so I don't know if you can hear this. You place it on the wall, you turn it on, and as you scan across, do you guys hear it beeping? The dielectric constant has changed, and now you know where your stud is behind the drywall. Okay, so this is an application of the ideas in this chapter. Y'all have used intermittent wipers before? That's another application. Your keyboard keys has them. And then capacitance is used in modeling how cell membranes and neurons work, for those of you who are in biology. Okay, and then you can use capacitance to measure pressure. You can use it as a pressure sensor. Okay, so you can use the idea to actually measure pressure. And you can do it fairly precisely, actually. Okay. All right. Let me do a couple of examples, and then I'll move on to chapter 28. And then I can answer your questions on the homework at the end. I just wanted to kind of get going, if you guys don't mind. If questions come up, just write them down and then bring them up at the end regarding the homework. Okay, so we talked about dielectrics and capacitors. And what they do is they increase the capacitance by a factor kappa. Excuse me. And I should say this is true for most materials. Okay, so if I insert a dielectric in between the plates of two capacitors, the field, as long as it's not connected to a battery, the field between the plates will decrease and the capacitance will increase because you have the same charge. Okay. All right, so what we want to do is a couple of examples. Like, let's say, suppose we have a parallel plate capacitor. Okay, and we charge it to some value Q, or Q naught. How much energy is stored in this thing?
Q naught squared over 2c.
Yeah, so we can write it multiple ways, right? We can write it like this. In fact, let me write it this way. Okay, it's going to be more convenient for me. Suppose now I insert a dielectric into the capacitor, and let me use the caveat that I disconnect this from I disconnect the battery from this and then insert the dielectric like I do here. How much energy is stored now? So I'll call this U initial, I'll call this U final. The capacitance will decrease by a factor kappa. Let me call that C naught. And I want to calculate the difference in energy.
Hey, Professor, you wrote the 1/2 twice for the Q naught squared over 2c.
Oh. Thank you.
Sorry, what do you say was the case when the capacitance decreases?
I'm sorry?
What do you say that was the case for that capacitance to decrease?
I put the dielectric in and the capacitance decreases.
Oh, so that's after putting the dielectric.
Yeah, this is after. Sorry, I have it backward because I didn't want to erase it because then I had to draw it again.
No, that's okay. Thank you. I just didn't hear that.
Okay, so U final minus U initial. Let's take 1/2 Q naught squared over kappa C naught minus 1/2 Q naught squared over C naught. What is that going to give me? Is that okay? So what happens to the energy?
It goes down.
It goes down. So what does that mean? So what does this mean?
Well, you had to do work to put the dielectric between the plates, right?
Well, the field did work, right? Like I have to do negative work to make it go in at a constant speed. In other words, this thing gets sucked in. The dielectric gets sucked in. Okay, so dielectric gets sucked in by the field.
Is that
Or
like
pulled in, I'll say
the
pulled. I'm sorry?
is that the effect of like the electric field beginning to polarize the molecules on the inside of the dielectric?
Yeah, what happens, and the way we normally describe it, at least at this level, we say, I mean, that's a good way to say it, is the field changed. The fields will start bending. And the effect of those fields changing and the outsides of the capacitor causes the dielectric to get pushed in. But it is due to the polarization of charge on the dielectrics. That's causing the distortion of the field. And you see a lot of different versions of this kind of question on problems. There's a video I did, and for some reason I thought it was not captioned, but it is. I forgot I captioned it. It is on one of the modules, the chapter 26. If you look on the chapter 26, not chapter 26, unit 3 module, there's a couple of links for chapter 26 videos, and I go through a problem similar to this. The one I go through is more difficult. And I actually calculate the force on the dielectric. Okay, so you may want to watch that. I'm sorry?
If we're doing negative work on the dielectric, does that mean we're moving it in the direction of greater potential energy?
If I'm doing that, well, it's like this, right? If I do negative work, if I lift up this marker, I'm doing positive work, right?
Right.
And now, am I storing energy?
In the form of potential energy, right?
Yeah, so I'm adding energy to the system when I do positive work. In this case, I have to do negative work. Otherwise, it's going to get sucked out of my hand, the dielectric. Okay.
Right. Okay.
Okay. All right, let's do another example. Suppose we charge a parallel plate capacitor to Q naught. We remove the battery and we insert a dielectric. This dielectric only takes up half the volume between the plates. I want to discuss the electric field, the potential difference, the charge density, and this capacitor. So I'm only going to, in this example here, I'm only going to talk about the effect, what happens to the capacitance. The video that I have on Canvas goes through all of this. It goes through all the gory details. Okay? Yeah, there's a lot of details in this problem, so it's in the video. So really what I want to do is kind of set it up. And then you can watch the video to see the entire problem. And then there's another problem in these notes that usually I don't have time to go through, but I did it in the video. Okay? So you can watch them both. So it's a little bit of a long video. It's like 20 minutes. But it's worthwhile watching. And you can always ask me questions about the video if you don't understand anything. That's the only drawback of doing videos is that you don't get immediate feedback if you have a question. So here's our capacitor. It has charge Q naught. And then I insert a dielectric. So it takes up half the volume. I'm not the greatest artist, sorry. And we'll just say kappa greater than 1. So half the volume is filled here, okay? So each plate has area A. So this plate has area A, so this has area A over 2. What happens when I insert the dielectric in between the plates?
Do you get two different values for the electric field?
Well, let's see. We do get the charge to rearrange on here and here, right? So I'm going to have charge here. The charge on this half of this half is different than this half. With Q left plus Q right equal Q naught. Right? You agree with me that this dielectric, because it gets polarized, is going to affect the charge distribution on the plate. Again, we're assuming the plates are very large, so that the charge here and the charge here are not necessarily the same.
If the battery hadn't been removed, would that statement still be true, that Q left plus Q right equals Q naught, or is that only because the battery was removed?
That's only because the battery was removed. If the battery was attached, of course the battery would be doing work, right? So the charge on the plates would be different. What would be the same is delta V. The delta V would be the same.
Okay, well, thanks.
Okay. Now, what can we say about the electric field? It appears that the electric field here and here are going to be different. Okay, now you're going to have, granted, the electric field is probably going to be different than what we started with. So initially we had this scenario. Initially, we had that scenario, and there was a field between the plates. It's probably going to be different here, but we need to say something about the field here and the field here.
Is it going to be the sum of those two is still going to be equal to the original field?
Why? I guess I'm not sure why that would have to be the case.
I don't know. I'm just spitballing.
Well, to look at this, I want to talk about the potentials between these two plates. Now, it is true that the field here is uniform, right? The field in between has to be uniform. No response means that somebody has an objection. Right? The field between the plates have to be uniform, here and here. These are big plates, right? So this potential is the same anywhere across here. So here's V1, here's V2. These are equal potential lines. V3, V4, etc. So I drew the equal potential lines. Everybody okay with that? These just represent equal potential lines in between the plates on the right-hand side. You get to the border, and what must happen here when you get to the other side of the border? Is the equal potential different? Is the V have a different value on this side? Is this equal potential different than this one? That's my question. The battery's not connected. Yes, Kai, the potential has to be continuous. So this one and this one have to be the same. this equipotential V2 prime is the same as V2, because otherwise you have an infinite force here. These are all the same all the way through. So these equipotential lines are the same all the way through. Okay. And of course, the conductors themselves are equipotentials. That means that the potential difference between these two here and the potential difference between these two here are the same. So delta V left equals delta V right. What does that mean? What does it mean if delta V left equals delta V right?
That the field is the same?
Yes, the field is the same. So let me write it this way. E left equals E right. What does this say about the capacitance? You have two capacitors next to each other and their delta V's are the same.
They're in parallel?
They're in parallel. So it means that you have two capacitors in parallel. So then C total is C left plus C right. Well, C left is going to be epsilon naught, half the area, over D, because the D is the separation between them, times kappa. And C right oops, there's no kappa there. So what does this come out to be? What's the total capacitance? Okay, Chase, I'm not, Chase, the battery's not connected. So you said you thought it was different. What's different if the battery's not connected? The potential? Well, the potential might have a different value than before. It might have a different value than this case. Okay. But what I'm saying is the potential here, the potential difference between these two and these two plates are the same. The delta V between these two here and the delta V between these two here are the same. I'm not saying that it's the same value as when the battery was connected.
Wait, so just to clarify, the two capacitors are the left side and the right side?
Yes, 1, 2, left, right, yeah.
Oh, okay.
Okay, this board is very hard to erase. Okay, so let's collect terms. I can write it like this. Check my math, okay?
That's good.
Looks okay? Now, here's the thing. If kappa was 1, what does this come out to be?
The same thing.
Same as this one. That better happen. Otherwise, I made a mistake somewhere. So in the video, I actually calculate E left and E right. I calculate delta V left and delta V right. And I calculate these two. And then I do one more thing, which is fun. At least I think so. Hold on. It's like the last slide. I do this problem. Okay, I actually calculate the force on the dielectric. So that's all in that video. And if you understand that, you understand everything about capacitance pretty much. Okay? All right, let me go back. I need one more example to do. And this one will be short. Suppose I set up this capacitor. Yeah, it is on the homework. Suppose we set up this capacitor. I want to calculate the force on one of the plates. And it should go by pretty quick, this problem. All right, so I'll put a dielectric. I'll put a dielectric in here. I've been making it red, so. And again, kappa is some number bigger than 1. How much energy is stored in this thing? Oh yeah, let's charge it up and then remove the battery. And I do the problems without the battery because they're a little bit easier. Because otherwise you got to consider the work done by the battery. So U then is going to be 1/2 kappa epsilon naught E squared A times D. This is the U for parallel plate capacitors. Okay? This is the familiar equation from the other day. I want to calculate the force on one of these plates. Suppose I lift up top plate by delta X. Okay, suppose I lift up the top plate by distance delta X. How much energy is stored? So U at D plus delta X, I can make it a dx, but that's okay. So now this is the energy stored. What's the change in energy?
Delta X times all that.
It's positive, right?
Yeah.
And delta U over delta X is 1/2 kappa epsilon naught E squared A. And in fact, if I take because this is constant, if I take the limit as delta X goes to 0, I still get the same thing, right? Do you guys remember what du dx represents from Physics 205?
The negative force.
Yeah, this is minus the force due to the field, right? So the force due to the field is actually downward.
What do you mean by downward?
Well, if I pull the top plate up, right?
Oh, well, doesn't that make oppositely charged?
I'm sorry?
Doesn't it make? Wouldn't we expect the force to point towards the other plate just because they're oppositely charged?
Correct.
Like they're attracting each other.
But this shows that, right?
Yeah. Okay.
Okay, that's the point. Yeah. So this shows that it's pointed downward, and it's a constant value is given by this. Oh, here's something interesting. What if you divide this by the area? What do you get? You guys remember what force per unit area means?
Is it pressure?
Yeah, it means pressure. So you can actually calculate the pressure. Now be careful, okay? Pressure and energy density are not always the same, okay? Because the pressure is going to be, in this particular case, but you know, this relationship, the fact that this is equal to the energy density is not always true. Okay, usually it'll be proportional to the energy density, but it won't equal the energy density. Just depends on the system. Okay. All right. So I wanted to do some of these examples today, just to illustrate to you. Well, just give you some more examples of how to apply these ideas to capacitors. Okay, and I think that these kind of problems help you to understand the physics behind capacitors. And usually these kind of problems are given in the homework as opposed to within the text itself. Okay.
Quick question. Where
Yeah.
did the D go when you have D plus delta X?
Well, we calculated the difference between this and this, right? Use the distributive law. Subtract them two. You see that?
Okay.
Okay. I kind of went to flow with that one because somebody said, oh, the D disappears. So I said, okay. I just wrote it down. All right, so let's go into chapter 28. And we've talked about chapter 27, and I think the beginning of chapter 28 should be fairly straightforward because we've covered series and parallel, etc. And I know I did this at the last minute, but I emailed you the notes for chapter 28 at the last minute. Oops, I messed up, sorry. Hold on a second. That's a good question, Chase. There's not really, I'd have to look at the trend in the textbook if there's a direct correlation between the dielectric strength of a material and the dielectric constant. And to be honest, I don't remember if there's a consistent relationship. The higher the dielectric, the higher the dielectric constant, the greater the dielectric strength. That I don't remember. Okay, because and I don't think you can say that just because a metal has an infinite dielectric constant. Okay, all right, because if you have a metal has an infinite dielectric constant, and its dielectric strength is not very high because it conducts electricity. Okay. So we are now at the point where we're getting charges to move through a conductor. So we're going to be looking at DC circuits. And we've done a little bit with Ohm's law. And like I said, I did Ohm's law early because of the fact that we had to learn how to use the multimeter. Okay, so that part, so I had to go a little bit out of sequence there. But at least now you know a little bit about Ohm's law. We are going to apply Ohm's law in circuits. And so I'm going to start off by drawing a circuit with two resistors. And again, a resistor is really any device that impedes charge flow. Resistors can be made in a lot of different ways. Usually when I talk about a resistor, I'm talking about something that's designed to obey Ohm's law, something that's designed to limit current, or something that's designed to produce a particular potential difference. Okay, like this circuit would be the perfect one to illustrate, a circuit that's designed to give you a potential difference. So I have two resistors in series, and the question is, how do I solve problems with resistors in series? And we're going to do resistors in parallel. Can I simplify the circuit? And again, I'm going to use ideal wires. And I'm going to try as much as possible, even though my figure doesn't show it, to use delta V's instead of V's, because really we're measuring, when we're measuring in a circuit, when we use a multimeter, we're measuring delta V's. So that picture should have a delta V in it. Okay, and I might go through and correct that and give you a new, just to be more technically correct. Okay. So I have two resistors there, and what I want to do is replace those two with a single resistor that really produces the same amount of current. Okay. And I didn't put these videos on Canvas, but that person named Electroboom, I know I always refer to this guy because he actually does great videos, but they're not all captioned. This person has a video on series and parallel. What they mean, and he goes a little more general about different kinds of circuits. But if you want to see his video, just do a Google search, Electroboom series and parallel, you'll find it. Okay. He also has one on Kirchhoff's laws, which we're going to learn about Thursday. So you might want to look at his videos. And like I said, I can't put them on Canvas because those are not captioned. I'm waiting for him to caption them. Actually, one of the two is captioned, I forget. One of them is captioned, the other one is not. Anyway, interesting in terms of, you're going to get the description of series and parallel from an electrical engineer. From their viewpoint, I guess. Okay, how they see things. Okay. So let's suppose that these resistors are not the same. I have a battery. Charge will flow. Electrons will flow this way, right? Electrons will flow. This is electron flow. They'll flow through the circuit that way. Now, whatever goes through this part of the wire, this part of the circuit, has to go through this part or this part. You cannot have the amount of electrons going through here be different than the amount of electrons going through there. That's impossible. Because otherwise, how do you account for them? Where do they go? Okay, I mean, just imagine water flowing through a pipe. Here's your pump. It's a closed system. and you measure the amount of water going through here and the amount of water going through there. If the amount of water going through here is different from the amount of water going through there, what does that mean?
There was somewhere where the water left or entered between them.
Yeah, you either have a leak in here or you have something, water collecting. And if water collects, these pipes will explode. Okay.
But can the amount of charge per unit time be different? Because otherwise, what is a resistor doing?
The amount of charge per unit time. Why would it be?
Obviously, all of the electrons have to go through, but if they're all going through as if there was like at the exact same rate, then what is the point of a resistor?
It reduces the amount per unit time going through it, right?
Okay, yeah, that's what I was asking.
Yeah, it reduces, but it reduces everywhere in the circuit. It just doesn't reduce it there.
Oh, okay.
It doesn't reduce it there, it reduces it everywhere. Because again, otherwise you will get an accumulation of charge, right?
Yeah, right.
So if you run this for hours and hours, then this part of the wire will burn, and then this one will not. Eventually, when this thing burns, your circuit's done. It's not just inside the resistors. Everywhere in your circuit gets affected. Okay, everywhere in your circuit gets affected. So if I constrict the water flow here, the whole thing gets affected. Okay.
Does a Venturi effect have any effect on something like this?
Oh, in this particular case, no. Not for electrons moving through a wire. No, it doesn't. It doesn't.
Okay.
Happen. Yeah, no. Okay, so the current through here and the current through here are the same. Now, the voltage drop across here then is I times R1. The voltage drop across this guy is that. So this is like at 0 volts, this is at 9 volts. This is at 9 volts, this is at 0 volts. This is going to be somewhere in between. So if you look at it, the potential difference between this point and this point has got to be equal to the sum of these potential differences. Right? If this is at 9 and this is at 0 volts, and this is at some intermediate value, then the sum of these two drops has to be equal to 9 volts. This is an example. So delta V, which is the delta V of the battery, is delta V1 plus delta V2. And we did the same thing with capacitors in series. Okay. So now I can replace these two resistors with an equivalent one. To give me the same current, and so R equivalent is equal to R1 plus R2. And I'm going to write a couple of equations here because people will get confused, especially on an exam. So I'm going to do capacitors and resistors. Oh, so what's C parallel? Okay, Are we okay with this? Okay, something happened. Give me a second here. Now, let me say something about resistors in series. Notice that the sum of the potential differences in a loop equals 0. In other words, if I go around the circuit, let's say this is at 9 volts, this is 0 volt. Let me make up a number. This is 5. Let's say this is 5 volts. Okay? Now, count with me. I go from 0 to 9. This goes up by 9, right? If I go from 0 to 9. If I just go all the way around, I go from 0 to 9. Then I go from 9 to 5, that decreases by 4. And then from 5 to 0, decreases by 5. They add up to 0. The sum of the voltage drop in any loop is 0. That's extremely important for you to understand. That is a consequence of the fact that the electric field in these particular problems are conservative. The sum of the voltage drops around the loop is 0. Does everyone get that? Okay. So what is it that you're not seeing, Chase? Right, I go from, let's say this is 0, that's 9. I go from 0 to 9, I went up 9. Then I go from 9 to 5, I went down by 4, and then I went down by 5. 9 minus 4 minus 5 is 0. So what is not clear about that? Yeah, because okay, let me write it like this. Is that better? Okay, right, because it's the same thing though, isn't it? But it's the reason why is because the integral of the electric field around a closed loop is always 0. The electric field is independent of the path. And this is called Kirchhoff's loop rule. We're going to make use of this on Thursday. Now, what about resistors in parallel? Or assume the two resistors are different. Now, what if we have this circuit? Well, because they're in parallel, we know delta V1 equals delta V2 equals the delta V of the battery. That we know. But again, like water flowing through a pipe, what happens when you reach this point, this node, this junction? Some of the water goes this way, and some of the water goes this way. So if this is I, this is going to be I1, this is going to be I2. That has to be the case. Otherwise, where's the other stuff go? So it must be true that I has to be equal to I1 plus I2. That's conservation of charge. Can't go anywhere else. But I1 is delta V1 over R from Ohm's law. And what I want to do is replace those two with an equivalent resistor. But delta V1 equals delta V2 equals delta V, and that gives me 1 over R1 plus 1 over R2 equals 1 over R equivalent. Like that. And notice the relationship between those two sets of equations on the board on the left. Okay, the reason why they're opposite, I mean they swap, they go like this, is because Q equals C delta V, and I is equal to delta V over R. So here C is in the numerator, R is in the denominator. By the way, C and R are two quantities that depend purely on the geometry of the system. We're going to learn about one more system like that. Okay.
So why doesn't power flow through the path of least resistance, though?
Why doesn't power go through the path of least? You mean current?
Yeah, current. I mean,
but it does, doesn't it? Why doesn't current does go through the path of least resistance?
yeah.
You say why doesn't it?
I meant the So why can't we just treat this as a single I know we're treating it as a single resistor now, but instead of it being R or 1 over R1 plus 1 over R2, why can't it just be the resistor with the least amount of resistance?
Yeah, you got to be careful. You got to take that with a grain of salt. It doesn't mean that all of it goes in one direction.
Oh, okay.
It means that the majority goes in one direction. So what that means then is if this is smaller, you'll get more current here than here. It doesn't mean that all of it goes through here.
Oh, okay.
Yeah, and that's a term that one has to be careful with. Okay. Yeah, I know. People will say current takes the path of least resistance, and that'll make people think, oh, it always goes this way, but that's not the case. Most of it more goes here than here. That's what it means.
Oh, okay.
Yeah. So the fact that this is true is indicative of conservation of charge, and it's another one of Kirchhoff's laws. It's called the Kirchhoff's junction rule or Kirchhoff's current rule. Sometimes it's called the junction rule. Sometimes it's called a law. Depends on the textbook. Okay. So you'll see abbreviations like this. Kirchhoff's voltage law, Kirchhoff's current law. Sometimes they'll call them rules.
Professor?
Yes.
On that slide, why was the sum of currents into a junction 0?
Oh, was it equal to 0? It basically means
yeah, it
whatever.
says that into any junction.
Oh, so let me take this equation. Can I and move the I to the other side? What do I get?
It is 0.
Okay, that's it. That's it. That's all it is. There's a different way of writing it, right? So I can say this.
Oh,
It's the same thing. So yeah, people write it different ways. It's good that you call that out, but they will write it this way. Whatever goes into a node equals to whatever goes out of a node. Or you can just say that sum of the currents equals 0, which means some are going to be positive, some are going to be negative.
okay.
Okay. But yeah, that's a good question. So as a review, these are the equations for resistors in series and parallel. So instead of doing a simple example with series and a simple example of parallel, why don't we do one that's just a combination? I'm sorry, my PowerPoint's freezing. Okay. Why don't I do a one that's a combination like I did with the capacitors? And again, I try to choose nice numbers so we can actually go through this problem pretty easily. Suppose we have this setup. Where do I start?
Probably start with the 12 kilo ohm resistors.
Yeah, and so what happens when I combine them? What do I get?
24 kilo ohms.
Okay, so I'm going to redraw the picture. Now, what do I do next? And maybe you might need to see the equation on the board. Let's see. So I would use the this equation, and yeah, you might need to do this with a calculator. But let me erase the bottom here. 1/8 plus 1/24. Can you guys do that quickly?
4/24.
4/24, and then take the reciprocal of that.
6.
So that'll give you 6 kilo ohms, right? So let me replace those two with another one. Let me replace the 8 and the 24 with a 6. Now I have 3 in series. 5 plus 6 is 11. 11 plus 9 is 20. So my final circuit, which gives me the same amount of current.
Jesus fucking Christ.
That was fast, wasn't it? That's it. Now guess what we can do? All right, 20 kilo ohms. We can go backwards and figure out how much current do I have. So let me go back. Let me write on the board. I need to write one more equation on the board. And then we can do this problem. Guess which equation I'm going to use? Ohm's law. So I is going to be 10/20. What's 10 divided by 20?
Two.
No, 10 divided by 20. It's a half. It's a half a milliamp.
Oh.
Okay. So we have half a milliamp. And we can calculate power. Power is going to be 10 volts times 20 kilo ohms. 10 volts times, I'm sorry, let me rephrase that. 10 volts times half a milliamp. 10 times 0.0005 is 5 milliwatts. Okay? Now, we can go back to the drawing. We can replace the 20 with the 3 that we had before. Each one of these resistors have the same current going through them. So each one of those resistors have half a milliamp going through them. There. For some reason my computer's really slow right now. Okay, so there you go. Half a milliamp through each one of them. How do you find the voltage? Well, let's see. The 6 kiloohms times half a milliamp, 6 times a half is what? Six times a half is 3. I got 3 volts. 9 times a half is 4.5. 5 times 0.5 is 2.5. So now I have the voltages. Now I can also calculate the power, because power is voltage times current. 3 volts times a half milliamp is going to give me 1.5 milliwatts. I'll get 2.2 milliwatts, 1.2 milliwatts. If you add up all the milliwatts, you get the same thing as 5 milliwatts. And granted, there's round off error, okay? Is everyone clear on that? Okay, so that 6 kilo ohm resistor replaced an 8 kilo ohm and a 24 kilo ohm resistor. They were in parallel, so the 8 and the 24 have to have 3 volts across them because they're in parallel. So 3 volts, the current is going to be 3 over 8,000 and 3 over 24,000. You add them two together, you get half a milliamp. Power is voltage times current, and you can calculate that. When you sum 1.1 and 0.36, and granted I rounded off, you'll get 1.5 like you did before, because energy has got to be conserved. That 24 kilo ohm resistor replaced two 12s, which means those two 12s have the same current going through them, and they'll each have half the voltage drop across them. And then power is going to be 0.36 across each one. So to do this, you draw the circuit, you reduce it down to a single circuit, and then work backwards to find everything else out. So Chase, yeah, the voltage is the same for capacitors in parallel. The difference, Chase, regarding the equations is the fact that, even though these equations look different for parallel, the voltages are the same. The difference is that C here is in the numerator, R is in the denominator. That's why these swap. And that's always confusing. Okay, so I want to do a demonstration. I don't think I have time to do this one. We'll see. I want to do a demo. It means I got to switch cameras. This is like. But I need you to participate. Okay. So give me a second here so I can switch cameras. So I disconnected the microphone. So I have a setup here. Can you guys see that okay? Okay, so I have 3 bulbs here. Okay, so I'm going to ask you some questions. This bulb is 25 watts. This bulb is, I know it looks small, is 60 watts. It's a ceiling fan bulb. And this one is 100 watts. They're connected in series. Which one's going to be the brightest? I'm going to turn it, I'm going to flip the switch. I have only one response so far. What do you guys think? What do you folks think? Small.
They're in series.
Yeah, they're in series. Should I flip the switch?
I want to say it's either all of them or the first one.
Okay. Why do you say, all of them? Should I flip the switch?
Because they are.
Go ahead.
I could be wrong. But just because they all provide the same amount of resistance to the current, so like the current is still going to be the same across all of them.
Yeah, the current's going to be you're right about that. The current's going to be the same, but they're all different. I mean, how do you know they all have the same resistance?
Which is each one again?
So this one's 25 watts. This one's 60 watts.
25?
Yeah, 25, 60, and 100. So
I want to say it's the first one, but then again, I have a feeling that it's going to be a trick question. It's going to be the last one.
Yeah, somebody else will say, well, it's the last one, but it could be a trick question. So, let me flip the switch. Okay. So which one is it? It's the first one, right? So you were correct in saying the first one. But why?
Because it's taken up all the... Like, it has more resistance than the other two, right?
Well, yeah, because they all have the same current. That one has the biggest resistance. That means that one has the biggest voltage drop. Now, you guys can't see it, but this is actually on a little bit. It's glowing. I don't know if you can see that. I mean, hopefully I don't get you guys dizzy.
Wait, I thought the one on the left had the least resistance.
This one does. No, this one has the most, sorry. Can you see if this one's glowing or not? Maybe not. Okay, let me put this back. Sorry. Hope I'm not making you guys dizzy. So this one has the greatest resistance.
Are you just inferring that using Ohm's law?
Yeah, just V squared over R, because these are all rated at 120 volts.
Gotcha. Okay.
Okay, so this one has the lowest, lowest power rating to the highest resistance. This has the lowest power, lowest resistance. Will it make a difference?
So that means it has the highest power rating.
Will it make a difference if I switch them? Switch them?
Yeah, it should.
Should? Okay, let's do that then. I'm going to put the 100 watt first. You want to put the 25 watt last?
Yeah.
Okay. That thing's hot.
I think they'll all light up just because now the current's flowing through all three of them, and the last one's just going to get what's left over from the first two.
Okay.
So they should all light up. Oh, never mind.
This is why I go through this demo, because that's a common misconception. Because, a lot of people were saying, oh, the current gets squeezed only through the resistor. This is illustrating that it doesn't get squeezed through the resistor. Right? It reduces it everywhere, not just through the resistor. The current's the same everywhere. It doesn't matter where you put them in the circuit. I can switch these two. I get the same. This one will still be the one that's lit.
Why? Could you explain that again if you already have? Sorry.
Well, the current's going to be the same for all of them, right? Charge has to be conserved, otherwise it accumulates somewhere.
Yeah.
Right, because if you say it's going to be more similar to another
But
case,
what's
you got to come for the fact, where's it going?
if the current is the same, what is the justification for why that one lights up? Does it just have a lower threshold for turning on, or
Or
what?
this one? Well, this has a bigger voltage drop. And you're right, it does require less power to glow. This only requires 25 watts. And it has the biggest voltage drop. Because it has the biggest resistance.
So is it just because there's not enough power or current supplied to the system? Like if you were to give it more energy, would all three of them turn on?
Yeah, let's do it this way. Let's try this then. So now, you tell me what the difference is. This thing's hot, jeez.
Well, now they're in parallel. I don't know.
Yeah, they'll be in parallel.
So what happens in this case?
They'll all have the same voltage across them, right?
Yeah.
Potential difference.
Okay, I gotta do one thing, otherwise it won't work.
So this might be kind of a dumb question, but what is it that determines like how bright each one is? Is it the voltage drop?
Well, it's both. It's the power rating. It's the voltage times the current.
Oh, okay.
So you notice what I'm doing? Without bypassing these, nothing goes on. How about now? You probably can't tell because it's on camera, but I could. This one's really bright. Okay? Because they all got 120 volts across them. In fact, if I take this one out, everything goes off. There's no power going through the circuit.
So when you're talking about the biggest voltage drop when they were in series, is that just by like the nature of the way that bulb? Is that something you can calculate based on that circuit specific?
Yeah, you can, because you can calculate the resistance. Right? It's I times R, right? The voltage drop.
Right. So what information? I'm sorry. What information did we know before you put any of the light bulbs in?
We know that this bulb was 25, this was 60, and that was 100 watts. And then I connected to the wall socket, which is 120 volts.
Okay, so you know the voltage and the power rating of the bulbs,
Yeah.
and then from that you can find the current and the resistance and stuff.
Yeah, I can figure all that out just from that information.
Gotcha. Okay, thank you.
Let me try something else. I'm going to put the 25 watt bulb here. 25. Let me put the 25. It's weird that this one's big and then this one's 60 watts and it's small, but it is what it is. And let's see. Let's have some fun with this. So this is 25 watts, okay? What I'm going to do is suppose I put another 25 watt bulb here. Now what happens?
I don't know if I understand the first setup well enough to guess about this one.
Well, let me take this out. Oh, that's not good. Oh, something got disconnected in the back. Let me unplug real quick, so I want to get electrocuted. Something got undone in the back of my board. I have a loose screw back. Okay, let me go back. I had the same problem last night. Okay, so these are the three This one has the highest resistance. So it has the biggest voltage drop across it. Just use I times R. Because they all have the same current because they're in series. And what I want to do is put a 25 watt bulb here. And the question is, what happens? This is barely lit, by the way. Ralph says I didn't see your question. If your question's above us. Hold on a second. So if P equals V times I, the one with the lowest power should have the lower resistance. That's correct. The one with the lowest power will have the lowest resistance. The one with the highest power will have the highest resistance. Is that okay, Ratesh? No, I'm sorry, did I say that wrong? The one with the highest power will have the lowest resistance. Okay, sorry about that. The one with the highest power has the lowest resistance. Okay, sorry. Yeah, the one that, okay, so let me say that everything again. Maybe I misspoke. But the 100 watt bulb has the lowest resistance and it will have the lowest voltage drop. The 25 watt bulb has the highest resistance and it will have the highest voltage drop. Is that okay? Okay. And I apologize if I misspoke. Okay. 100 watt has.
I think you just.
I'm sorry?
I was just saying, I think you just switched to the two, but it makes sense now.
Okay. So now what if I put this 25 watt bulb in the circuit?
It's going to get the same voltage, right? So it would be just as bright.
What happened?
Oh, do you treat it as a new resistor with lower voltage because of the reciprocal thing, and so it gets lower resistance because of the reciprocal, and then so it's not as bright.
Yeah, these two are parallel. So one of the things you should notice about the parallel equation, when you have two resistors in parallel, the equivalent resistance is lower than either one of the two resistors. So the total resistance between the two has gone down. That's why this is brighter now. So you have a lower resistor here. Maybe not as low as this one. For sure not as low as that one. Although that's starting to glow now.
If I were to plug in like a 30 watt one right there instead of one that's of the same exact power rating,
yeah,
they would be different brightnesses, right?
Yes.
Okay.
How about if I put a 100 watt here?
They would just be a lot dimmer.
Well, in fact, if I put 100 watt here, the parallel combination is going to have a lower resistance than this 100 watt bulb. Look at that. 100 watt, 25 watt. Okay.
So because they're reciprocals, the effective resistance of those two is just really, really low, so they're not bright at all.
Yeah.
And so then, why does that make the other bulb brighter? Is it because that one becomes a higher percentage of the total effective resistance?
This one does.
Yeah.
Yeah, this one does, yeah. And this is the second most.
So if I have if I have two resistors in series, then if one of them is like 100 ohms and the other one's 1 ohm, then the one that's 100 ohms is just going to be a lot brighter.
Yes.
And then if I plug in like a 0.5 ohm in the place of the 1 ohm, then it's going to get even brighter then.
Yes.
Okay.
Right. The 100.
Wait, that last part confused me. If you plug in a 0.5, I thought you said 5. Never mind, not confused.
Chase, what's your question? Maybe, Chase, you might have to go through the math, because I'm going through it conceptually, and so maybe if you actually sit down and solve the circuit mathematically, then you'll start seeing it. Sometimes when you don't see it conceptually, maybe just solving the problem, just say, okay, I have 120 volts into my circuit, and I'm going to be dividing 120 volts amongst these 3 bulbs. Yeah, and I'm hoping that what I said was enough, right? Because I said this is 25, that's 100, that's 60. So one thing you can do is draw that at home. That'll help you keep track. If you maybe take out a piece of paper, draw the circuit, and say this is 25. What is it? This was 100 watts. This is 25 watts. This is 60 watts. Just draw a picture, and just say you have 120 volts going into the system, and then see which one has the biggest voltage drop. And that way I think you might see it better. If you don't see it mathematically right away, then sitting down and doing the problem will make a big difference. And then when I put this 100 watt in my circuit, that makes these two smaller, and that makes the combination of these two smaller than that one. And that's why this one becomes the brightest, because now the voltage drop is greatest across this one. So you got, somebody brought up, let me go to a different camera, sorry. One thing I want to say before I'm done, I know I've went over, sorry. And I apologize for screwing up the voltage thing, or the resistance thing. I want to go back to the series circuit. Use a better marker. Just treat the bulbs as 3 resistors. And so the current is going to be delta V over R1 plus R2 plus R3. If I had a multimeter to measure the voltage across R2, the voltage drop across this one, R2 is going to be this current times R2. So this is, a lot of people call this a voltage divider circuit because when you have resistors in series, this splits up the voltage in different ways. So this splits up the voltage 3 different ways. It divides it 3 different ways. Okay? So the bulbs are dividing the voltage 3 different ways when they're connected in series. Okay, so delta V R1 is going to be delta V for the other one. So now we say that the bulb with highest power rating, I'll write it down so I get it straight. Has the lowest resistance. And so the bulb with lowest power rating will have biggest delta V, biggest voltage drop in the circuit. The 25 watt bulb has the biggest resistance, so it has the biggest voltage drop. Okay? Questions on that? Concerns? Let me turn my demo off. It's like one of my favorite demos because people have so many misconceptions about how they work. What is it that I said is wrong, Rakesh? The one with the highest power rating has the lowest resistance. So the one you're saying that the one with the highest power rating has the largest voltage, but the 100 watt bulb didn't even go on. Yes, but P is also V squared over R. Those bulbs are rated at 120 volts. You are correct, but the bulbs are rated at 120 volts. The P assumes 120 volts. You know, the number you see on the bulb assumes you have 120 volts across the bulb. Okay. Are we okay then?
Wait, why isn't the delta V squared? Oh wait, because that's the voltage drop.
Yeah. So when we did the lecture on chapter 27, I did a problem at the end of the chapter, and we said, you know, light bulbs are rated at 120 volts, so you have to use this equation. This number, the number that's on the bulb, is based on 120 volts across it.
Oh, okay.
Okay. That's what it's based on. It's based on, okay, because otherwise it's going to be something different when you have a different voltage across it. Okay. We're okay with that then? Okay. So I'm going to do a couple more examples with series parallel, and then I'll do Kirchhoff's laws on Thursday. Questions on the homework?
I actually had a question on the lab, if that's okay, or do you want to do?
Yeah, go ahead.
Oh, okay. So I'm looking at the first part, and like it seems like I think you said it was vague on purpose, but I'm not really sure how to go about, like, it says determine how the bus lines are connected on the proto board.
Well, I showed you in the video, right? What you had.
Was there a separate lab video from the lecture?
No, I just showed you in the lecture. You just got to measure the resistance between any two pairs of holes.
Oh, okay. So that'll give us like a path or something.
Yeah, you'll see a trend. You don't have to do every single pair that's on the board. You'll notice a trend right away.
Oh, okay.
Yeah, don't do every single one, but do. You might need to do 5 or 10, and then you'll be done. You'll figure it out.
So then we're like drawing the line from the like sort of the way the circuit board is wired, or
Yeah. So if I'm going to draw the circuit board. So here are the holes, right? And I'll get to your question in a second, Ralph. So you draw a line indicating, are they connected this way? You just draw a line like that. Or are they connected this way? Just draw a line like that. That's all. You got to see how they're connected together. You'll see a pattern like that.
Oh, okay.
Because you're not going to if you're going to use it to wire, you don't want to make it hard on the electrical engineer to wire the circuit. You want to make it easy, right?
Yeah.
So if there's a distinct pattern, it's an easy pattern to see. All you got to do is measure resistance between holes.
Oh, okay. Thanks.
Okay. So basically what I said in the video, just in the lecture, just stick wires into 2 holes and measure the resistance between the 2 wires. So, Raft, as you said, does the capacitance increase in a vacuum? That's a good question. So this equation assumes vacuum. This equation for capacitance assumes we're in a vacuum. Every problem that we've done up to the middle of chapter 26, we're in a vacuum. Okay. So when you go in a medium other than a vacuum, then this goes up. But the speed of light goes down. It turns out that the speed of light depends on epsilon. And when we do magnetism, there's a similar quantity for magnetism. And the speed of light is related to it too. Okay, so question number 14. 13 and 14 are related to each other. Okay, and then we'll look at 10. Actually, Ratej, you're almost the same. I mean, within like a percent maybe. Yeah, the breakdown voltage in air depends on how humid it is. Yeah, the breakdown voltage in air depends on how humid it is. The more humid it is, the lower the breakdown voltage. That's why the labs, probably the chart lab, does not work very well in Florida, especially in the summer. I would never have you guys do the property charge lab if we were taking this class. We were in Florida in the summer. Okay, so number 14 and 13 is the same. So you have coaxial cylinders. And in between you have a dielectric between the coaxial cylinders. Now, we know the dielectric strength. And we know the dielectric constant, I think, right? Well, there's a gas, so we're going to assume it's the same as that of a vacuum. So, we know that the electric field between two concentric cylinders is this. Okay? I'll get back to your breakdown voltage. Let me go through this and I'll get to your breakdown voltage question. The potential difference, we talked about this the other day, is given by this equation. That makes us positive. Okay. Now, question is, we want to know the maximum delta V we can apply to this Geiger counter before it breaks down. Okay. Granted, this is a wire, but I'm drawing this as a thick wire. So we know the breakdown voltage. I'm sorry, the breakdown field. Meaning the field you have to get when it breaks, when it arcs. The question is, to make sure this works okay, at which value of R do you want this to break down? Which value R do you want to choose? You want the big one or the small one? If you choose the big one, then anywhere inside here is going to break down, right? Because you want to find the maximum potential difference that you can apply before a breakdown occurs. Don't you want the small one? That's going to make this number bigger. If I choose the biggest one, then it's going to make it smaller. I can put less charge on it. Software 2K land, I put it in here and you're done. Is that okay? 13 is the same way. Yeah, I'll get that to Aiden. I just want to make sure I get that one, and then I have the question regarding the breakdown voltage and airing. So Chase, is that okay? Okay. So number 10 is a little bit harder because let me just finish up with Rob said about 10A. Let's see. Yeah, Ratesh, regarding your question. Yeah, as long as there's moisture in the air, the breakdown voltage decreases. But the capacitance in a vacuum is slightly lower than in air. Okay. So to do 10A, you can ask yourself how much work it takes to bring that first plate. Okay. How much work does it take to bring in the first plate? 0. Now, what about the second plate? How much work does it take to bring in the second plate? Second plate is not 0. Now, we can assume that these plates to be big but not infinitely large. So we can use the approximation that the field is sigma over sigma. The field into each place is sigma over 2 epsilon naught. Okay. So you're doing work against this field. This will be plus sigma minus sigma. And bring it from infinity and putting it here. You basically have a capacitor. Okay, you basically have a capacitor. You can calculate the work this way. This is going to be the energy stored. The other way to calculate the work done, if you assume the potential at infinity is 0, these are not infinitely big, you can say that you're putting them on charge Q, and you're moving it through a delta V. You can write down the amount of work that you do on this plate by this equation. So there's multiple ways, or you can just say this. Which is the energy stored. Now, you know that the field outside of here is 0. All right, the field here is 0, the field here is 0. Maybe I should have written here. Okay. Let me erase this. I should write somewhere else. Because I want to bring the other plates in. Let me draw the field lines for each of these. The field here is 0, the field here is 0. I bring in the third plate. No work is required, so no work for this one. No work for this one. The only one that requires work is that one. And then I bring in the fourth plate. But now, when I bring in this plate produces an electric field. Let me bring in the last plate. I'm going to use orange. No, I'll use purple. I will use orange for this field. So here it feels non-zero. So you can work on this one and you can work on this one. But don't you really have two capacitors, Aiden? So you can do the following. You can say, oh, well, the work is going to be 1/2 C up to V squared times 2, or you can say that the work done, which is again stored as energy, is going to be Q delta V plus Q delta V. Where the Q is the total charge on any one of those plates. Was that okay? So for part C, well, Chase, I mean, how are they connected to a wire though? I mean, you gotta tell me how you gotta be careful in terms of how they're connected. Okay. So for part C now, what you got to do is, and again, I would just say for part C, I would calculate the amount of work is required to arrange this, bringing them in one at a time. So calculate the work for this one, and then calculate the total work for this one, and then take the difference. Yeah, I don't know how long it takes for the video to upload to Zoom. This one's going to take a while because we're already at the 2-hour mark.
Okay, so like if you post it today, it's probably gonna be there by tomorrow or something.
Yeah, the one on Zoom will probably be there by this evening. The one I upload will take longer.
Yeah, no, I'm talking about like the one you upload to Canvas. Not the one on YouTube.
Yeah, the one on Confer Zoom is automatic. So
Oh, okay, cool.
yeah, I guess 1 or 2 hours after the lecture.
All right, awesome.
I thought it'd be more than that, but maybe I'm wrong again. So I don't know. Are we okay? I think the other ones are okay. It's this one that causes the most headaches. Number 10. All right, if you don't have any more questions.
I had a question on 9. If that's okay.
Yeah, go ahead.
Okay, so I also went over this one with Tyler, and for some reason, when we were both doing the calculation, we got the wrong answer for part B. So I found the electric dipole moment, and I did the I found the torque by doing the r vector of each one crossed with the force each one experiences, but he told me you can do it by crossing the electric dipole with the electric field.
Yes.
And so like we did it both ways, and we both got the same answer, and it said it was wrong.
For part B?
Yeah, for part B.
Okay. Do you want to calculate the torque, P cross E?
Yeah, it was the one with the torque.
Right. So is that an issue with you taking calculating the cross product, or?
I don't think so. I mean, I think we did the cross product right because we both got the same answer. Do you think maybe you could do you think I can give you my numbers, and then you can see if we screwed up somewhere?
Well, go ahead. Yeah.
Okay, so
Can you put it on
the chat?
or share your screen, or?
Oh yeah, I can share my screen. Can you see that?
Yeah, it's a little small, but let me see if I can get real close. Okay, so where's your work, I guess, on? So you got part A.
Oh yeah, I was doing my work on a piece of paper.
Oh, okay.
I don't have it on screen.
Well, I can write it in terms of piece of
Yeah.
X and piece of Y, if that's okay.
Huh?
I can write it with just generically.
Oh, okay.
It could be that you just round it off.
Yeah, and then this answer I have right here, it wasn't the one I got originally.
Does it want the magnitude, or does it want? I'm sorry.
It wants the vector, so like it's a negative answer.
Okay, so it only has X and Y components, right?
Yeah.
Let me just make sure. Okay, so the only thing that's going to survive is whatever that comes out to be.
Here, wait. Can I stop sharing my screen so I can see your screen?
Ahead.
Oh, okay. All right, cool. X, Y. Yeah, that's what I did, but marked it wrong.
Marked it wrong, huh? So let me check your WebAssembly real quick.
Or wait, maybe I'll enter what I got originally. Yeah, Chase, that's what I did. I put it I made sure to check the direction.
Okay. And you because I'm looking at your response. It's quite a bit bigger than the answer they have.
Oh wait, never mind. I'm dumb. I didn't see the negative on the electric field.
Okay.
Yeah, sorry about that.
Okay.
Professor,
Yeah.
I missed what you said for C. You said like I just forgot what you said for C.
For 10C,
Yeah.
so what you got to do is go back and see how much work is required to set this one up. Okay?
Okay.
And take the difference between this setup and the setup in A.
Okay. Thanks.
Anything else? If there's nothing else, then I guess I'm gonna end it. So yeah, this video will take a while to upload, so I apologize. It's at least the one on YouTube. I don't know how many of you folks watch the YouTube version, but it's there just in case. When the internet's bad, the one on YouTube is better. All right, so I'll see you folks in lab on Thursday. Have a good evening.
Thank you.
All right.